Hi guys, Nick here with BitGalaxis bringing you a new video on Unity 3D game programming, and today I wanted to show you how you can calculate planet gravity, and we're going to build a very basic system for Unity 3D, and then we're also going to talk about some of the considerations that we need to have in regards to when we make gravity based on planets instead of having it on a plane. So what do I mean by on a plane? Well, by default in Unity, when you have a rigid body, you are putting gravity calculations on it that are based only on the y-axis. So you attach a rigid body to a game object. So in this example, we have a cube. And when we've attached a rigid body to this cube, we give it a mass, and we just leave the defaults. By default, it's going to use gravity. And what does that mean? Well, that means that every object is going to fall down. And so when I say it's on a plane, what I really mean is everything goes down on the y-axis. So its y value is going to decrease until it collides. So in this case, once our box hits a plane, it's going to stop. And that's Unity's default behavior. But if we have a planet, for example, and we want objects to be attracted to that planet, suddenly we have a very different need. And so what we mean by this is, let's say in the previous example we have this box and we want it to fall down. Well, in this position right here, it's perfectly fine. It's going to fall down and it's going to go to the center of the planet. But that's only because of its position. If the box were to be to the left, it would fall down and fall into space. Whereas this box here would also fall down. We want it to be attracted to the center of the planet. So one consideration you need to have is when you put a rigid body onto an object and you want it to be attracted to something, you have to uncheck the box to use gravity, because by default Unity is always going to make that put a force down. And if you forget to check this or uncheck this box and you're applying your own custom gravity calculations, then you're not going to get the behavior you expect. So how do we calculate gravity? Well, let's think this through. What do we need? We need a force that pulls our game object in the direction of the center of mass of the planet. And how much force? Well, if we're using fixed update, we want to use Earth's gravity is 9.81, and this is going to be a float value. Moon's value is 1.62, and then we also need to multiply it by our object's mass. So in this case, the rigid body. So what direction do we need to apply this force? Well, it's going to be our position relative to the planet's center of mass, but we want to normalize that. And what does normalize mean? Well, normalize means that we're going to take the direction and we're just going to say I have a total vector length of 1. So imagine just that direction, but we're just pointing 1 in that direction. So we're basically just pointing at it with a default value of 1. So we have the direction, but we do not have a length. So why is that important? Well, it's important that we do that because if we want to apply a consistent value, such as 9.81, and our mass, well, if you don't normalize your value, then the further away from the planet you are, the faster your object's going to fall because it's going to have more force. And then the closer it gets, the less force it has. So you just want to make it 1, and then your mass, and then your gravity value. So let's simplify that. So our force is going to be our direction times 9.81. So we're going to use the Earth's gravity, and then we're going to use we're going to multiply those together, and then we're going to multiply that by our get component rigid body dot mass. So I don't actually know if you can put this in Unity 3D and have it work. I'm just kind of saying if we didn't have a variable that we use for our rigid body, we want to grab that rigid body and then get its mass, and that's for our object. The direction then is going to be a vector 3, and it's a normalized vector that takes our position and subtracts the position of the planet, and that will get us a position relative to us. Okay, so I've got Unity open here, and I've set up a scene with a few objects here, and I'm going to go over this setup real quick, and then we'll jump into some code after we demonstrate how our gravity works. So in this scene, I've just got a giant sphere, and I have a sphere collider on that. It does not have a rigid body because it's just a static object, so no need for a rigid body here. And then I've got this little buggy up here in space, and it's going to fall down regardless. It's above the sphere, but it's also got some wheeled colliders. It's got a rigid body. You can see here the rigid body has been attached to the parent object I've got my camera rig, so I can just attach a camera behind it. Real simple way of setting it up. And then I've got my mesh, and I've got some colliders on the wheel colliders and some other colliders attached here. But really, the rigid body's here. My mass I've set to 5,000. I do not have gravity, and I have gravity here at 9.81. So let's go ahead and actually demonstrate what it's like with the default gravity value. So I'm not going to put a gravity value here because there's no need for it. In reality, if I have gravity here by the default, then this gravity is not necessary. Unity is going to calculate its own gravity. So we're just going to take a look at what happens if we play this with the default Unity gravity. And we start out, and we are falling, it's just hard to tell. And now if I start driving though, and it takes a little bit, it's not a very slow vehicle, it's going to fall. And that's it. I'm driving real slow, and I'm falling, and I'm spinning, and you'll see that the planet is really, really far away by the time we get to it. So there you go. You can see it's way off in the distance. So what's happened here, if we zoom out and go back to our sphere, we have basically driven off the edge and then fell down. Went straight down, and we kind of spun a little bit, and then we were looking back up at the planet as we got there. So let's go back to our buggy. We're going to turn off use gravity, and we're going to set our gravity here to 9.81, which is the same gravity as Earth. It's also by default the same gravity value that Unity uses. So now what's going to happen is this gravity value that I've entered here, which I'll show you the code in just a minute, actually does say, so what's going to happen is this gravity value here is actually going to say use a force and put the force of this object in the direction of the planet. So you can see here I have a gravity target of the sphere, so that's there on purpose. You can do this many other ways. This is just a quick and dirty way of getting the target object to be the force we're pushing to. But let's go ahead and test out this script. And our buggy's falling, lands on the planet. Now what happens if we push forward a little bit? I have just a little simple input. The shadows are always off a little bit, and I'm not sure why that is, but it is actually touching the planet. So as you see, as we go around, we're going around in circles, and I can turn a little bit. I have a little bit of torque, and I can turn this just a little bit. You can see we're sort of turning. You have to use the horizon to tell that because the planet's just uniformly a bunch of triangles. So, but you can see we're driving around now. Now we're on the underside, and our buggy is continually just driving over the surface. And if I turn too fast, I start to roll, and I actually even start to fly off the planet a bit because we're moving fast enough that we're kind of already entering orbit since this planet is so tiny. So I'm going to kind of reverse a little bit to slow down if I can. It's not helping. I'm starting to fly off a little bit. Let's go ahead and talk about what our code is and how it works. Here is the simple code that I have. Now I've got my transform of the gravity target. Remember, this is in the inspector. I dragged in the sphere into the inspector and said that our planet was the target. We have a power for this is all vehicle related. The power and the torque are for my turn values and my thrust values on the buggy itself. But then really what matters here for us for the purpose of the gravity is the gravity value here, public float gravity 9.81 F. So we also have a rigid body, and this is for the object itself. And we're going to use two functions here. We're going to use start, and at the start we're going to grab the rigid body, and that's going to be our get component rigid body. And this is saying let's grab that rigid body for physics purposes so we can run our calculations on the physics. Then we're fixed update. We're going to process the input. So all this is doing, I have some process input code. If you want to look at that, just kind of take a screenshot of it now, and you can use that. But I'm going to close that because this isn't the focus of the video. But we're processing the input, and then we're also going to process gravity. In process gravity, I am declaring this vector3 diff, which is just short for difference. And that's going to be our transform.position minus our gravity target.position. So that gravity target, the planet, we're getting its position. We are subtracting it from our current position. So we're basically saying, where is the planet? And that's what that is. Now, our rigid body add force. So we're taking that rigid body and we're going to add a force, and it's going to be negative. Just basically saying r vector 3, the difference, then normalize. And again, the reason why we normalize it is because we don't want to have the gravity be higher when we're further away and smaller when we're closer. We just want it to be a constant value. So we're going to take it times our gravity, which we declared up here is 9.81, and then we multiply it times our rigid body, which we got here, same thing here, our rigid body's mass. So why do we need to do it by mass? Well, if we don't do it by our mass, remember we have momentum. So gravity is always constant. So smaller objects fall at the same rate of speed as larger objects. The only difference is if there is like air resistance or other things. But in this case, a small object should fall as fast as a big object. And if we want to do more complex calculations, we can. But in this case, we just want it to fall at that rate like we expect it does on Earth. Then I just have a little debug draw ray that's just, I can inspect to see which way is our force actually applying. So really, what code do you need to calculate the gravity? It's really just this. And so the final result on this is what you see here on the space buggy. We've got our gravity. Again, we grab that sphere. So I just here pick this, drag the sphere in there. I've set this as power and torque is only for the vehicle itself, but the gravity itself I set on the object. And so when you press play, the end result is I've got some power. I thrust forward a little bit, and I can turn a little bit, and I'm sticking to the planet. It does look like I'm leaving the planet because of the lighting, but in reality I have not left the planet yet. You can see the gravity here shows that I'm still on it. I'm not sure why it does that, but yeah, now we're traveling around the planet, and we are basically just maintaining our position right on the surface of the planet. So one thing we're going to talk about is how this fails. Okay, so back in our presentation, I've set up an image that kind of might explain why using a car or a box or something with a flat surface that moves is kind of just a lucky way of getting our object to align correctly with the planet, as long as it doesn't leave the surface. But let's walk through why that is so that we can get an idea of what kind of problems we might have with perhaps a character collider, which is not going to have a flat bottom. It usually has a capsule collider. Here you can see I've got this box and it's on its corner, right? Now, because we have gravity pulling it in to the center of the planet, it would actually make this box fall flat on its surface, just like it is here and here. So one potential issue we might face is, what if the box jumps? And let's say that the box jumps up and over like this. Boom. So with the gravity as I have it right now, it would actually do exactly this. If I were to jump and then have it move around the planet, it would actually move like that. Not exactly, but the point I'm trying to make here is the box was on its bottom and now it's on its side. Why is that? Well, because I made a force that pushed it up and then a force that pushed it over, and it kind of rotated and fell back down due to gravity. But there is nothing to force the object to rotate. The only reason that our vehicle always stays on the correct orientation is because it's always on the surface. And so as the vehicle moves along the surface, all four corners are touching, and then as it moves forward a little bit, then it needs to rotate down, but gravity's already pushing it down because it hasn't really left the planet. So it's just a matter of the distance that we're moving, how quickly we're moving, things like that. If we were to leave the surface of the planet, then we would not be able to control our rotation or make it match gravity. So there are a couple of concerns about that, and how you address those is kind of up to you. But I'm going to give you a very basic setup to be able to address that. Let's go ahead and jump into some logic here and some code. So how do we address the object orientation? So what do we need? We need a way to rotate the bottom of an object to always face the planet. So when we jump, when we leave the surface, we want the bottom to land back on the surface. So let's talk about calculations for a minute. We're going to use a Quaternion orientation. And so what you'll see in the code that I'm going to show you once we demonstrate it is we set a variable Quaternion orientation direction. So what I'm saying is, which way do I want my object to face? And how I'm calculating that is we are going to get quaternion from to rotation. So what this means is, how do I rotate myself from my down value to the down value to the planet? And it might return, oh, you have to turn 15 degrees on the x-axis, or 15 degrees on the z-axis, or maybe even 15 degrees on the y-axis, or a combination of those things. What you can see here is I have what it would take, the rotation I need to do to make that motion, but I also have to multiply it by my transform rotation. Why is that? Well, because my current rotation isn't 0. My current rotation could be anything. So in order to find, so this from to just says, well, how do I get from this angle to this angle? And it's going to say, well, move this many degrees along x, y, and z, and that's my rotation. But you also have to do it from your current rotation. You have to consider your current rotation. If you're at 0, then this is no problem. So then I say here our value for rotation. So we're going to set our current rotation on the object, in our case the buggy, equal to a Quaternion.Slerp. So I'm not going to go over Lerp. Lerp is basically just a method for how you can kind of smoothly change a value instead of just like, oh, we start moving and we stop moving. It's kind of like, oh, we kind of ramp up and speed up and slow down depending on how quickly we get there. But Quaternion.Slerp is the way of doing this for rotation. You want to use Quaternion.Slerp opposed to just a Lerp generally when you're doing rotations. So because rotation is very different from translation. So use Quaternion.Slerp. So just remember this is Slerp for rotation, or I'm sorry, just remember this is Lerp for rotation. And we're going to say that our current transform rotation is where we want to rotate from, and then our orientation direction, so where we're going here, which we calculated up here. And then I also have an auto orient speed, so I have a value saying how quickly do we want to auto orient, so our value for automatically orienting our buggy to have its bottom face to planet, and then we're going to multiply that times our time value, so our time step. So we're kind of always forcing it to face the planet at a rate that we decide. So again, just kind of going over those bullet points again, determine how much we have to rotate, Quaternion from to rotation. And again, why do we multiply by our object's transform at the end? Because our rotation could be anything. We don't want to assume our default value is 0 because we're in space. And we also smoothly rotate the object to match the orientation. Again, use Quaternion.Slerp. Alternatively, you can use Lerp, but for rotation, Quaternion.Slerp is better. So let's go ahead and go back into Unity. Okay, so here we are back in Unity, and I'm going to, I've added some updates to my script to do our auto rotation. And just to show you how that works real quick, I'm going to go ahead and click on our little space buggy here, and I'm going to rotate this on X to 90 degrees. And what we're going to see as it falls, we are going to see it kind of just automatically rotate so the bottom faces the planet. We're going to reduce our gravity to about 0.5 so it falls really slow. Well, I thought I deleted everything out of there, but let's do that. And we're going to check auto orient. This is a little button I've added so we auto orient. We can turn this off if we need to. And I'm going to also reduce the auto orient speed so that Lerp, or that value for how quickly we rotate, I'm going to reduce that down quite a bit to about 0.2 so we can kind of see that we slowly orient. And there's some other tweaks we might do later, but for now, this is what we're going to do. So as we fall, what we should see is that now the buggy is actually orienting towards the surface. Now we have really low gravity. By the time we get there, we've already made our bottom face the bottom, and then we bounce a little bit when we land. And it doesn't look like we're actually landing on the surface. Again, I think there might be a lighting issue with that. I'm not real sure. But if I rotate and move and things like that, then I am going to see that the buggy will rotate around and eventually just stick to the rotation of the planet. And I think I have too much force being applied right now, or my auto orient speed is too slow. So I'm going to go ahead and I'm going to increase that, and you can see the auto orient speed, it's automatically doing that now. Let's increase our gravity so we land, and now we are definitely sticking to the ground, and we are definitely always going to be flat. If I reduce gravity again, no matter what happens, my buggy's always going to face the bottom. If we go back into our scene view, kind of look at it, just zoom in, we can see that our butt's facing the, I don't know how to stick with it. It's facing the planet, so we're going to stop. Oh, maybe I can just go back in there. But again, as you see, auto orient speed, if I bring this up, we're going to basically flip real quick. We're going to, basically be flipped as soon as we get there. So you want to make this a pretty low value because you do want to have those forces still being applied. You make it 1, it'll be kind of slow. And we'll increase gravity a bit. And there we are. So that's the quick and easy fix for the things. Let's go ahead and look at the code. Okay, so here we are in the code, and what we're going to look at here real quick is adding these options for auto orient is what I call it, and I just have a bool to check whether we are or not going to orient our object to the planet. And then we're going to set our auto orient speed. I would say 1 or 2 is the most you need. You go any higher than that, it's going to be pretty quick, and you may not even see it. So we haven't changed our start or our fixed update or our input, but we did. So again, from fixed update, we're calling process input and process gravity. What I went ahead and did, I figured, well, it's always going to process gravity. If we have auto orient, it's based on that gravity. So we might as well just call it from process gravity. So I've created this auto orient function, and then from process gravity, we actually call it. And so process gravity hasn't changed, except we added this one line. And that one line is if auto orient, so if it's true, then we're going to call the auto orient, and we're going to use negative diff. Remember, again, diff is the difference between our position and the planet. And so we're just saying that's going to be our down. So we are changing our position as a positive. We want it to be a negative because we're pointing down. So we're passing negative diff is equal to r vector 3 down, not the object's down, but down from the object to the planet. So remember, kind of like in space or when you're looking at a space shuttle, the space shuttle could be upside down. Its down is actually way out in space, while its back, or like let's say that the top of it is actually facing the Earth while it's in space. So we're taking that down value from where, from our position to the planet. Down is to the surface. So again, we're calling that Quaternion orientation direction. So really this should be orientation rotation. I should just rename this, but I'll leave it as is. But we're saying, what do we have to do? What's the rotation going to be? And the rotation is going to be our Quaternion from to rotation. So again, Quaternion is just a way of calculating rotations. And again, we have to do that times our transform dot rotation. Why? Because our position, our current rotation, may not be 0. We're going to set our current rotation equal to a slurp between where we are right now and where we want to be, which was calculated up here. So where we're going to go, we're going from here to here, and we're going to do it at this speed, and then times time dot delta time. That is how the code works. Again, just to demonstrate, if we were to press play on this right now from the scene, we'll see, based on those current values, that our bottom of our car does start to turn to face the planet. And then if we go back and increase the gravity on this, which we're looking at here, then we'll take the gravity down a bit and go back full speed again. But you can see we're now facing it. I wonder how much gravity I need to get. Whoa, see, now we're spinning and it automatically reorients every time. So that's another thing too. You could also use this same process. Like let's say that you have a car like in GTA and it flips over and you want it to reflip after a certain amount of time. You could use this function, but you wouldn't necessarily have to do it towards gravity. You could always just do it vector 3 dot down for the world space. And that's one instance where it would be useful to have a vector 3 dot down as a comparison. So you can always make sure your cars flip right side up whenever you're in a game. So Anyway, this would correct our problem. If you had a character that did not have four wheels, they would also rotate up correctly, and your controller would then just have a surface to work off of. It would rotate correctly. You might want to actually have that audio orient speed be higher so that your character can never be crooked. Like, let's say, for example, if this was a person walking and you just had them moving around the planet, they might fall over. And depending on their speed, you'd want to have that rotation happening pretty quickly. So anyway, that's all I have for today, guys. I hope you liked the video. If you did, please go ahead and hit the like button, subscribe if you'd like, and I hope to see you next time. Thank you for watching.